Our modern world thrives on communication. We send messages, share experiences, and access information instantly, thanks to the invisible highways of radio waves. These waves, carrying our voices and data across vast distances, are the domain of RF signals. But before embarking on their journey through the air, these signals begin their life in a different form: baseband signals. Understanding the distinction between these two fundamental types of signals unlocks the secrets of modern wireless communication. Imagine the raw, unprocessed information flowing through our devices, the music stored on our phones, the vibrant colors of a video, or the lines of code in a program. This is the essence of baseband signals. They represent data in its original form, occupying a low-frequency range, typically starting from 0 Hz and extending to a few megahertz. This range is ideal for handling information-rich signals over short distances, such as within electronic circuits or cables. Think of baseband signals as the raw ingredients of a delicious dish. They hold the potential for a flavorful experience but need further processing to be enjoyed fully. Similarly, while crucial for internal communication within electronic devices, baseband signals lack the ability to travel wirelessly over long distances. Their low frequency limits their range and makes them susceptible to interference. Enter RF signals, the seasoned travelers of the electromagnetic spectrum. Occupying a much higher frequency range, typically from a few megahertz to several gigahertz, RF signals are the key to unlocking wireless communication. They are generated by modulating, or imprinting, the information carried by baseband signals onto higher frequency carrier waves. This process is akin to attaching a letter to a carrier pigeon, enabling the information to traverse long distances. These high-frequency carrier waves act as vehicles, carrying the baseband information through the air. This ability to propagate wirelessly makes RF signals ideal for long-distance communication, forming the backbone of technologies we rely on daily. Section 4. Baseband versus RF: A Tale of Two Signals. The key difference between baseband and RF signals lies in their frequency and, consequently, their applications. Baseband signals with their low frequencies excel in handling information-rich data over short distances. They form the foundation of wired communication, operating within electronic circuits, cables, and optical fibers. RF signals, on the other hand, with their ability to travel wirelessly over long distances, have revolutionized communication. They are the driving force behind radio and television broadcasting, satellite communication, Wi-Fi, and cellular networks. Section 5. Why RF signals reign supreme in wireless communication. The dominance of RF signals in wireless communication stems from their unique characteristics. Their high frequencies allow for efficient transmission and reception using antennas. These antennas, acting as gateways between the wired and wireless worlds, convert electrical signals into electromagnetic waves and vice versa. The higher the frequency of an RF signal, the smaller the antenna required for effective communication, making them ideal for portable devices like smartphones. Moreover, the use of different frequency bands within the RF spectrum allows for simultaneous transmission of multiple signals without interference. This principle, known as frequency division multiplexing, enables us to enjoy a multitude of wireless services concurrently. Section 6. RF signals in action, from radio to satellites. The applications of RF signals are as diverse as the information they carry. Radio broadcasting, one of the earliest forms of wireless communication, relies on RF signals to transmit audio content over vast distances. Television broadcasting utilizes RF signals to carry both audio and video information, bringing entertainment and news into our homes. Satellite communication harnesses the power of RF signals to connect even the most remote corners of the globe. Satellites orbiting Earth act as relay stations, receiving RF signals from ground stations and transmitting them back to other locations, enabling global communication and broadcasting. The Global Positioning System, or GPS, relies on RF signals transmitted from satellites to pinpoint our location on Earth. By analyzing the time it takes for these signals to reach our GPS receivers, the system can accurately determine our position, revolutionizing navigation and location-based services. Wi-Fi, the ubiquitous technology that keeps us connected within our homes and workplaces, relies on RF signals to create wireless local area networks, or WLANs. These networks allow devices to connect to the internet and each other without the need for cables, providing seamless connectivity. Cellular networks, the backbone of mobile communication, utilize RF signals to connect our smartphones and other mobile devices to the global telecommunications network. These networks rely on a network of cell towers that transmit and receive RF signals, enabling us to make calls, send messages, and access the internet from virtually anywhere. Section 7. Bridging the gap. Appreciating the interplay of baseband and RF. While distinct in their characteristics and applications, baseband and RF signals are not mutually exclusive. They exist in a symbiotic relationship, working together to facilitate seamless communication. Baseband signals provide the raw information, while RF signals act as the carriers, transporting this information across the airwaves. Understanding the interplay between these two fundamental types of signals is crucial for appreciating the complexity and ingenuity of modern wireless communication systems. As we become increasingly reliant on these systems, a deeper understanding of their inner workings will allow us to better utilize and appreciate the invisible highways of radio waves that connect our world.